Welcome back, everybody. We are looking at exercise 1 on page 140 of the workbook. This is another exercise of calculating the divergence of a vector field. And exercise 1 is broken up into two parts. So there's a part A and a part B on the next page. Basically, part A is asking us to examine the three vector fields that they're giving us pictures of here and to graphically see if we can figure out whether divergence is positive or negative. And then in part B, we'll be confirming our answers algebraically. Okay, and before we dive into this, let's remind ourselves of what this notation R means. The vector R is just shorthand notation for the vector field xi plus yj, the one that has radial symmetry away from the origin. Okay, and what I'd like to do together is to see if we can work through parts 1 and 2 of A and B. They kind of go together. Okay, and then I'm going to leave parts 3 and 4 for you to look at. See what you can do with those. All right, so if we start this off, let's read part A together. They'd like us to use graphical reasoning to decide whether each of the following quantities are positive, negative, or zero. Okay, so let's start with the divergence of F at 0, 0. F is the field over here on the very left. Okay, so talking about the divergence at 0, 0, is like visiting this point here, and we're going to be talking about the flow out of a small shape that's centered at the origin, and that shape could be anything. I'm going to choose a circle, closed circle, just because this field has radial symmetry. Okay, and the question that we're asking is, would we be getting net outflow or net inflow into that circle? Okay, well, you can look at the vector field and see that the vectors appear to be pointing out of that. Okay, they're flowing out of this surface, and so the divergence should be positive because we've got net outflow. All right, so let's go ahead and state that answer here. Okay, that's positive. Okay, because there's net flow out. Of a small disk centered at the origin. Okay, again, divergence is positive if we're getting net flow out of whatever curve or surface we're talking about. All right, so that's number 1. Okay, and then number 2 is asking us to go over and look at the vector field G, which is sitting over here in our diagram. And the point of interest in this case is 1, 1. Let's mark that point. So that's sitting right about there. So we need to draw a closed shape around 1, 1. And there's no radial symmetry in this particular field. So I'm going to draw a little square instead of a circle, just because that's a little bit more of a convenient shape to analyze here. And we're going to ask the same question. Are we getting flow into that little square that we drew or out of it? Okay, well, the first thing that you might notice is that our vector field doesn't have any x components to it. It's entirely vertical, so there's certainly no flow in or out of the left and the right side of that little box that we drew. What about the top and the bottom? Okay, well, there we could start by maybe looking at our vector field and how it's behaving. So focus on the right side of the box and just the vector field lines kind of on that side of the box. So you see how all of them have the same length, okay, as we look at a vertical line. So what that tells us is that we're going to get the same flow into the bottom of the box as we are out of the top of the box, because the length of those vectors doesn't change as we move along a vertical line. If you move over to the center of the box, kind of the same thing. The vectors are a little bit shorter on that vertical line, but we're going to get the same flow in the bottom side that we do out the top. And you can work your way across right to left and see that that observation holds everywhere. Okay, on a vertical line, the vectors all have the same length, so we're going to get the same flow in the bottom as we do out the top. What would that say about the divergence then? Well, if you think about it, it means that the divergence has to be 0 because of the fact that we're getting the same inflow in the bottom as we are outflow in the top. The net is 0. Okay, so let's see if we can put that together into one statement here. So the divergence is 0. Because the flow into the bottom, okay, of the square we drew, and I'm just referring to the diagram above, is the same as the flow out of the top. Okay, so the inflow equals the outflow, and so the net is 0, okay, giving us a divergence of 0. Okay, so we've done parts 1 and 2 together, and I'd like to move on to part B and see if we can algebraically confirm those answers. Okay, so let's scroll up here. All right, so we're going to be looking at parts 1 and 2. Those deal with the vector fields f and g. So let's maybe start by reminding ourselves what the formulas for those fields were. So f looked like xi plus yj. That was the f of r equals r. And g looked like just xj. All right, so let's calculate the divergence algebraically here. The divergence of f, okay, using our formula, would just be the partial derivative of x with partial derivative of the first coordinate with respect to x, partial derivative of the second coordinate with respect to y. So we're going to get 2. Okay, and then for g, same idea. There is no I component, so we're taking the partial derivative with respect to x of 0, and then partial y of x. That's going to give us 0. Okay, what's interesting is there are no variables in those two quantities that we got. So what it tells us then is if we go back to part 1, we were interested in finding the divergence at the point 0, 0. But x and y being 0 is kind of irrelevant. We're going to get 2 every time. So if you substitute 0 and 0 in, you're going to get 2 out. Notice that that's positive. Does that agree with the answer that we got back in part A? Let's sneak a peek. Sure enough. So we reasoned out graphically that that should be positive. We have just confirmed that algebraically. Okay, and then the same thing with 2. The divergence of g, this time it was at the point 1, 1, but again, we just got a number. Doesn't matter what point we're at, we're going to get 0 according to our calculations. Does that agree with the answer that we got above? Okay, sneak another peek and notice it does. Okay, we got 0 when we kind of reasoned graphically. Okay, so now it's your job to see if you can finish the other 2 parts of this problem. Okay, kind of the same thing that you're doing in 3 and 4. See if you can complete parts A and B for the vector field H.